I want to present a package I wrote with Eduardo Grossi together a couple of months back. And so, as the name suggests, it's about interpolation, and it's about interpolation with pseudospectral method on certain domains I'm going to explain to you. So, first of all, maybe the question, why another package? I guess the FastOPInterpolation interpolation package is relatively common, and it was also our inspiration to write this. The simple reason is we wanted essentially the same things, so pre-calculate a lot of functions and evaluate them even more while maintaining full flexibility and control, so manipulate everything essentially whenever we want. But our big problem was that our domains are not hypercubes or hyperrectangles, meaning unfortunately we can't use this package, but we need different geometries. So to give you a very simple example, where this is relevant for us, so we typically encounter equations that look like this. So you have some objects, and then they appear in integrals on the right-hand side. We have to calculate adaptively. And then these domains of these variables in the end turn out to be cylinders, prisms, tetrahedral lines, or something like that. And then unfortunately, we don't only have like such a small system in reality, but we have like hundreds of equations with like thousands of terms inside the integrals on the right-hand side, which is why we want to interpolate. So how does it work with pseudospectral methods? So we pick up via collocation, so we pick up a bunch of points here on the function and calculate our function there. And then we want to represent simply this usually expensive to evaluate function with some polynomials. Orthogonal polynomials are nice because in a sense they're optimal. They give you spectral convergence, meaning if you add more points, you exponentially get better in representing the function you interpolate. And then the big task is here to represent your function simply by a bunch of coefficients, and then your polynomials called phi here. And given that you have here some nodes xi where you evaluate everything. So you can simply rewrite this as a matrix problem, like your function equals some matrix times your modes. So in order to access these modes, the big question, the only task essentially is to invert this matrix. This is a rather well-known problem. These matrices are called Vandermonde matrices and are simply the polynomials evaluated on the nodes where you know your function. And this immediately determines where you actually want to evaluate your function, because if you just pick equally spaced nodes, for example, like equal sampling, the conditioning of this matrix diverges exponentially, so you can never invert this matrix for a reasonable number of points. But if you pick up different points, for example, Chebyshev points in one dimension, it only grows logarithmically and you can invert huge matrices easily. Then to evaluate this, you can evaluate arbitrarily high orders of orthogonal polynomials as stable and extremely fast. So they have three-term recurrence relations, which you can just unroll internally. So you scale linearly with the degrees of freedom, which we also tested up to a couple of 100,000 of degrees of freedoms in our code. And then everything is floating point stable. So floating point errors never accumulate in these relations. And one nice thing is in all of this business, it factorizes over geometries. So if you combine geometries to some larger dimensional geometries, everything factorizes. For example, if you have two of these Vandermonde matrices which you need to invert, there's a Kronecker product in between, and then inversion simply, well, you have to invert them individually, meaning you only ever deal with sort of medium-sized geometries. So what's currently implemented in the package, there are three base domains available. A line, so the most common one, I guess. Then triangles and disks. And then we have essentially large classes of polynomials for all these geometries. So in a line, you can just pick up any Jacobi polynomial you want. So Legendre, Chebyshev, and all the others. On the triangle, it's currently Kornwinder type 4 polynomials, and on disk, Kornwinder times 2 polynomials, and the package provides you already nodes for line arbitrary order, and for a triangle up to order 18 of the polynomial, which, for example, you can see here for some lower order of the polynomial how they are spaced, so always towards the edges of your domain. And the same for the disk, where they're known up to order 30, and they're giving in big float notation also if you need that in your applications. Then you can combine these domains in arbitrary fashion as you want. So if you need these such interpolations on, for example, prisms, you just take a triangle and a line. For a cylinder, you take a line and a disk. You can, of course, build hyperrectangles, but you could also build more crazy stuff. So you can combine lines and two disks, for example, to build something 6-dimensional, unfortunately, which I couldn't visualize. How do you use it? Well, it's extremely simple and straightforward. So let's say you have some function. You simply define your domains. So you have to specify corners. All the mappings are getting done for you internally to map everything to reference elements. Then you set up your interpolation element by simply combining these. It returns you an interpolation object and then the nodes where you should evaluate your function in each domain. You can also, for convenience, directly give you the tensor product of your nodes, which then become large matrices. And then your typical loop would be you evaluate your function on all of these nodes simply. Then you call a single function called update interpolation. And it carries out the internals. And then you can simply call this your interpolated function as much as you want. And in this case, for example, if you have some simple function, like something like a sinus, of course you reproduce it exactly, even with like moderate-sized polynomials here. So what's to come? More base domains, of course. This will be very soon because I need them for my personal research. So tetrahedra and spheres, to just name two. The other big thing we are working on, which unfortunately might take a bit longer, is currently you can't use autodiff in this entire setup to produce derivatives of your evaluations because the performance comes from using internal buffers to unroll all the nested recursions that appear in these polynomials, but we're working on that. And if you have any feature requests like more polynomials or want to participate in any way, please just contact me. Yeah, thanks a lot.
Thank you so much. Any questions? We have time for a couple.
Do you think it would be straightforward to do it?
Yeah, that should be possible, actually. So the problem with these domains is always a bit, polynomials have to be known on these domains. So if anyone ever figured out polynomials for these domains, then it's no problem.
And then the sine function example, did you compare the speed of the sine function versus the interpolated function?
Not systematically, because you would need then to figure out sort of it's not our use case to represent simple functions, even simpler in a sense, but to reduce it for external, really expensive. Yes, exactly.